Dear students, in this class we'll discuss deformation of cube of rigidity of modulus. In last class we have discussed the deformation of cube of bulk modulus. We got the equation that is k equals to 1 divided by 3 into alpha minus 2 beta. So that is equation 1. Now we'll find the next equation for the rigidity of modulus. So let us take one cube of the material, that is here we'll apply a force as tangential to that cube. So that face is indicated with A, B, H, G. So here that force is a shear force or tangential force. So that tangential force is applied, then what will happen? The relative displacement takes place. So that relative displacement is A dash and B dash. So these relative displacement will makes an angle theta, that is angle A dash D and B dash C we can call. Otherwise AD A dash and B C B dash. So now here this is triangle is equal to the theta. So here I have written. Now we'll write the tensile stress. So how the tensile stress is arises here? Whatever the tangential force is applied, that is nothing but the tensile stress here. So how it is, we'll see later. Now the tensile stress is equals to the force is applied to the area of ABHG. So the area is ABHG. The each of the cube is length L. So that is L, and then area of the ABHG is L square. So this is gives the tensile stress, or it is maybe tangential stress, or it is called as a shearing stress. So now this is called as the length of each of the edge of the cube. And now the relative displacement is takes place. A dash is equals to the B dash is equals to the length of L, small l. So therefore from this one and then original length we can find the shearing strain. Shearing strain, that is change in the or relative displacement is divided by original length, that is nothing but the theta. So we'll use this one and this one in a next upcoming relations. So now we can write the modulus of rigidity, that is tangential stress divided by shearing strain, that is equals to the eta equals to T divided by theta. By using this relation we can find the second equation, that is modulus of rigidity by the deformation of the cube. So now what we'll do here, what happen if we taken a box and apply a force to that cube, and then what will happen, the relative displacement will take place, and then how the relative displacement will take place and which direction will take place. See here, from the D to B dash, from the D to B dash the extension will take place, and then A to C that compression will take place. So these two of the compression and extension will use to produce the deformation in the body. So that deformation is used to change in the shape of the body. So how the deformation will take place here? See here now, whatever this shearing stress is there, this shearing stress is equals to the extension for that dB dash. That force is called as tensile stress. So that is equals to the tensile stress. Shearing stress is along the AB, and then tensile stress is along the DB. Both are equal to each other, and also is equals to the compressive stress along the AC. Compressive stress along the AC at the rigid angle to the each other. Sorry, right angle to each other. And now here we will take for the extension, that is alpha, and then for a compression we will take a beta. So we will see now the extension and compression along the dB here. So now the extension along the dB, the equation is becomes dB along the dB, and tensile stress is applied to that dB, and the extension will take place, that is alpha. So this is extension along the dB. So similarly the compression along the dB will get, that is dB into tensile stress along the AC here into a beta. So why beta is a compression along the that AC. So here this AC is there, after applying the force will get the A dash C will get. So now here what will happen in the body, total extension how much along the dB will find here, total extension along the dB, that is equals to the dB into tensile stress is into alpha plus beta. So therefore now here what is the dB is a diagonal, so the right angle triangle here, see here this is a right angle triangle. For this right angle triangle the dB becomes that is diagonal, that value if you calculate it, then what you will get, L into root of 2. So therefore the total extension along dB is equals to the L root of 2 into T into bracket alpha plus beta. So this is the equation 1 will give. So now here what we'll do, we'll take a data diagram. So now what we'll do here, we'll draw one perpendicular line on a dB dash. We'll draw one perpendicular line on a dB dash, we'll give here, this is the E. So now here A, B dash and C are nearly equals to the A, B dash, C, the nearly equals to the angle 90 degree. Nearly equals to the angle 90 degree. So therefore the angle of B dash is equals to the 45 degree. So here this is a 45 degree. So now what is there, the extension, how much extension it will produces from D to B and D to E is equal length, both are the equal length, and after this one will get the extension, that is a E B dash. So how much extension will takes place, we'll find that is E B dash equals to the see here I know the B dash into angle cos of 45 degree. So now here B dash is a small l, and then cos of 45 is nothing but the 1 by root 2. So therefore E B dash is equals to the L by root of 2, that is equation 2 I will take. From equation 1 and 2. So what is the equation 1? Equation 1 is nothing but the root 2 L root of 2 into T into bracket alpha plus beta. So equals to the L divided by root of 2. So root 2 get cancelled, and now we'll write the equation, that is T into bracket L divided by small l equals to the 1 by 2 sorry, here it is not get cancelled because it is multiplied. So if you multiply, then what you will get? You will get that is 2 into bracket alpha plus beta. So therefore now beginning only I have written, that is a tensile stress divided by theta is equals to the, what is that? Theta is nothing but the small l divided by capital L. So therefore this equation becomes now, what is that? Eta. So now the eta equals to 1 by 2 into bracket alpha plus beta. So this is called as equation 2. So this expression is called as the deformation of cube of rigidity of the modulus. So and now see here, I have written here, and now eta equals to 1 by 2 root of 2 into bracket alpha plus beta. So that is called as modulus of, we'll write here, modulus of rigidity or rigidity of modulus. So now similarly here the third equation, that is Young's modulus equation. Here what will happen, only one direction force is applied, that is tangential force is applied, okay, and now the extension is also along the A, B we have taken, and then what will happen here, that force is a 1 unit I have taken, that is the tensile stress is a 1 unit, and then the extension is alpha, the extension is along the only one direction, that is alpha. So therefore if we imagine the cube of unit edge is acted upon the by unit of tensile stress along the one edge, and then extension produces is alpha. So the stress is 1 unit, tensile stress is 1 unit, and the longitudinal or linear strain is alpha by 1. Why? Because 1, the original length is a 1 and change in the that extension, that is alpha. So therefore alpha will get, and now Young's modulus y equals to normal stress or a tangential stress, tensile stress divided by linear strain. So that is equals to the 1 divided by alpha. So therefore y equals to 1 divided by alpha. So now we'll call this is equation 3. So equation 1, the equation 1 is, that is a bulk modulus k equals to 1 divided by 3 into bracket alpha minus 2 beta. So this is the equation we have derived, and then next eta equals to 1 divided by 2 into bracket alpha plus beta. So equation 2 have derived, and equation 3 is y into bracket y equals to 1 divided by alpha. This is equation 3 we have derived. So using 3 equations we will derive the relation of an elastic constants, relation connecting the elastic constant. So how will we get the relation connecting with each other for one and another, we will derive in next class.